Okay, so now I'm going to talk about some relationships between stability functions and exponentials. Okay. And so you might ask, well, why would you expect to have a relationship between stability functions and exponentials? And sort of quick answer to that is because stability functions come from looking at how numerical methods behave when you apply a numerical method to a linear differential equation. And of course, the solutions of linear differential equations can be expressed in terms of exponential functions. So that's, again, immediately suggests that there might be some sort of relationship between stability functions and exponentials. So let me sort of make this clearer. It's like by stating the following lemma. So suppose that you have a solution sequence. Okay, so yn, then n goes from 0 to infinity, right? Which is produced by applying a method of order p, right, to a linear equation with constant step size. I should say what the linear equation is, right? Y dot is equal to lambda y with constant step size. Sort of satisfies the condition that basically yn is equal to r h times lambda applied to y0, while r h lambda to the nth power applied to y0, right? Then necessarily, right, it has to be that r of z is equal to e to the z plus big O of z to the p plus 1, right, as asymptotically as z approaches 0. Okay, and the proof is straightforward, right? So you know that yn plus 1 in particular is equal to r h lambda times yn. Okay, that's really the definition, if you will, of the stability function, is that the update the numerical method it's like when applied to this linear differential equation exactly has this form, right? And we know that the exact solution is basically y at tn plus 1, right, is equal to e to the h times lambda applied to y at tn. Okay, then right, subject, well, okay. Then really it's like by the definition of local error in order of accuracy, right? These two things it's like have to differ, it's like by something which is big O of z to the p plus 1, right? So r of z is equal to e to the z plus big O of z to the p plus 1. Okay, so this is really just sort of a straightforward observation. And again, it just comes from the fact that on one hand, it's like the stability function is telling you something about what happens to the numerical method. It's like when you apply it to a linear differential equation, and the exponential, it's like does the same thing for the exact solution. All right. Okay. Okay. Anyway, so so given that, let's just look at these stability functions. Okay. So in particular, we say that the stability function R that satisfies this approximation condition, right, which is that RZ equals e to the z plus big O of z to the p plus 1, is said to be order p. So you should be a little bit careful when we say that the stability function is of order p, right? Because it's like one might be tempted to say, well, you know, let's look at the stability functions, check its order of accuracy, and then conclude something about the order of accuracy of the original numerical method, okay? And that turns out to not necessarily be a good thing, because all you've really done when you compare the stability function to the exponential is more or less you've checked the order of accuracy of the method only for linear problems, right? So you need to be cautious, right? As this only tells you about the error of the method when applied to linear differential equations. So in particular, just because the stability function is order p does not mean that the underlying one-step method is of order p. Okay, so so it is possible to construct sort of p-order accurate methods with stability functions R that has order higher than p. What that basically means is that you could have numerical methods of order p for generic problems, but when you happen to apply these methods to a linear system, it achieves a higher sort of faster rate of convergence. Okay, so so in any case, it's like it's still interesting to ask how you can look at these stability functions. Okay, so let me now state a theorem which basically tells you what are the highest order stability functions you can have. It's like in the form of a rational function. It's like with a certain degree numerator and a certain degree denominator. Okay, so let me state the theorem as follows. So you're given any integers, alpha and beta, both of which are greater than or equal to 0, then there exists a unique function. Let's call it r hat, alpha beta, okay, in the space of rational functions of degree alpha beta. So alpha corresponds to the degree of the numerator and beta corresponds to the degree of the denominator, okay, such that, okay, you have r hat alpha beta, right, is equal to the numerator p hat alpha beta and q hat alpha beta, right, with the property that q hat, well, q hat alpha beta at 0 is 1. So this is just some sort of normalization-like condition, if you will. It's like which then uniquely specifies p hat and q hat. Otherwise, of course, you could multiply p hat and q hat by any non-zero constant. It's like and still get something which gives you the same r hat, right? All right. So you want this. It's like and with the property that r hat alpha beta is of order alpha plus beta. Okay, and again, if you recall, it's like what that means is that r hat alpha beta, right, approximates the exponential with an error which looks like big O to the z to the alpha plus beta plus 1. Okay, so that's basically what we mean by saying r hat alpha beta is of order alpha plus beta. Okay, and this perhaps isn't so surprising, right? If we were, instead of looking at all rational functions, we were just looking at polynomials, then it's like, this might be just, it's like the truncation of the Taylor expansion, for example, right? Okay, so, but except now it's like we have rational functions, but nevertheless, it's like, it's perhaps not so surprising. Okay, so okay, then you can actually write down explicit expressions for basically p hat and q hat, which are the numerators and denominators, right? So the explicit form of the numerator, let's call that p hat alpha beta, and denominator q hat alpha beta, right, given by, okay, so p hat alpha beta as a function of z is the sum from k equals to 0 to alpha. Alpha choose k, then alpha plus beta minus k factorial divided by alpha plus beta factorial z to the k, and then q hat alpha beta z is equal to the sum from k equals to 0 to beta of beta choose k, right, alpha plus beta minus k factorial divided by alpha plus beta factorial minus c to the kth power. Okay, and you can sort of see that these two things look very similar, and indeed they are. So this is equal to basically, well, let me write it this way. It's related to p hat, right, beta alpha minus c. Okay, so if you look at it, right, if you see it, it's like here you have an alpha, here you have a beta. Every time you see an alpha, you have a beta. So there's the swapping of the roles of alpha and beta, and then instead of z, you have minus z. Okay, so basically it's like that allows you to conclude that q hat alpha beta at z is equal to p hat beta alpha at minus z. Okay, and you can sort of readily verify it by just the form of these two expressions. Okay, so basically then, so moreover, right, r hat alpha beta is the only member of the rational functions with degree alpha beta that is of order alpha plus beta, and no function in this class may exceed this order. And I should say that, well, it's only, well, up to sort of rescaling of the numerator and denominator, right? Okay, so it's sort of the obvious thing. Up to, it's like, you know, multiplicative rescaling, it's like of P and Q. Okay. All right. So that's kind of interesting. And so this has a very special name, right? So it's a special kind of approximant, if you will. These are called the Padilla approximants of the exponential. So I should sort of say that, right? So these are the Padilla approximants, P-A-D-E, with an accent on the E. Of the exponential. Right, and you might imagine that there are similar Padilla approximants of different types of functions where you're looking for the best element of a sort of space of rational functions with a prescribed degree for the numerator and denominator, which maximize the order of accuracy, right? So, but since we're primarily interested in approximating the exponentials because of this result we had, it's like relating stability functions with exponentials, we're going to focus on these Padilla approximants of the exponentials. Okay. And it turns out that many of the stability functions we've seen so far are examples of Padilla approximants. Okay, so if you look at r hat 1, 0, right, this is 1 plus z. You've seen this, it's, I guess, one of the stability functions, I think, for the Ford-Euler method, right? There's this r hat 1, 1 term, which is 1 plus 1/2 z over 1 minus 1/2 z. And this, if I recall correctly, is the stability function for the trapezoidal rule, for example, right? And then we saw this r hat 1, 2, right? It's just 1 plus 1/3 z over 1 minus 2/3 z plus 1 over 6 z squared. And this was the stability function for these two sort of implicit Runge-Kutta methods, which we saw. Okay. So you can ask, it's like, you know, for Padilla approximants, you know, under what circumstances they are A-acceptable, which basically means that they are potentially good candidates for A-stable methods, right? Yes. Okay. So there's some obvious conditions. So one is that you need that alpha is less than or equal to beta, right? So basically, you can't have that the numerator has a higher degree, and the basic idea is that if the numerator has a higher degree, then more or less there's a remainder type term. It's like, which is, you know, if you think of doing synthetic division, it's like there'll be a term there which depends on z, basically, right? And that, of course, is going to, the modulus of that is going to go to infinity. It's like as you approach, you know, as you, while you're on the left half plane, but you sort of go away from the origin. So you need alpha is less than or equal to beta for basically r hat alpha beta to be bounded on the negative half plane, right? So that's a necessary condition for A-stability, but there are sort of other conditions. Okay, so this is not sufficient. So in particular, there's a counterexample to this. You can check that r hat 0, 3, right, is not A-acceptable. Okay, so it turns out there's a nice theorem which tells you, you know, when these Padilla approximants are A-acceptable. Okay, and so this is due to Warner, Hire, and Norset. So let me just state that theorem. Okay, so the theorem states that, so this is Warner, Hire, and Norset. Okay, and it states that the Padilla approximant R hat alpha beta, right, is A acceptable if and only if alpha is less than or equal to beta, which is less than or equal to alpha plus 2. Okay? And then there's a corollary of this, right, that the Gauss-Legendre implicit Runge-Kutta methods are astable for all s greater than or equal to 1. And that just follows from the fact that it's like the order of the stability function is a upper bound, if you will. It's like for the order of accuracy of the method, right? So we know that, so the proof of this is basically that the Gauss-Legendre and implicit Runge-Kutta methods have order 2s, right? So the order of Gauss-Legendre is 2s, right, for s stages, okay? And you know that the stability polynomial, it's like for an s-stage Runge-Kutta method, right, is in general, so R, it's like associated with this Gauss-Legendre method, has to be in the space of polynomials of degree s, right? So they have, it's like a numerator which has at most degree s and a denominator which is at most degree s. Okay, and then it's like this other lemma we had. It's like is that the Padilla approximant of degree ss, right, is of order 2s, right? So R hat ss, right, is order 2s, and it's the only element of PSS which has that order up to the scaling of the numerator and denominator simultaneously. So this implies that, all right, and I think the other thing you have to say is that R has order 2s as well, right? At least order 2s, right? R has order at least 2s. It's like, and that's because Gauss-Legendre is 2s order accurate, and so when you restrict it to linear problems, it has to be at least order 2s accurate as well, and so that means R has order at least 2s. So then by the uniqueness result, that means that R is equal to R hat ss. Okay, and then the Warner, Hire, and Norset theorem says that R hat ss is A acceptable, right? By the theorem. Okay, so all these things together then tell you that the stability function for the Gauss-Legendre method is A acceptable, which means the Gauss-Legendre method is A stable. So this implies that Gauss-Legendre is A stable. All right. Okay. So so that pretty much covers our discussion of sort of A stability for Runge-Kutta methods, and then the next thing we're going to do is to look at what happens with multi-step methods. So let's just stop here for now.